So let's talk about the assignment from yesterday. Now here's the main idea. So when you have something moving in a circular path, Mother Nature actually doesn't like circular paths, even though a lot of things move in circles. Mother Nature prefers straight lines with a constant speed. So if you look and see anything moving in any kind of circular path, okay, whether it's a planet, whether it's a rubber stopper being swung around on the end of the string like you can have like this,
It's
okay?
an unholy abomination.
Huh?
It's an unholy abomination.
Okay. All right.
That's
That's a
where you're
bit,
going with that, right?
that's a bit harsh, but we can go with that. So, because in any given point, if you, and this is why you have to look at Newton's three laws in conjunction. You just can't isolate one law. So the first law says, hey, Mother Nature wants to maintain a constant velocity. If you remember that there's two parts to velocity, there's magnitude and direction, then you realize, oh, if something's changing either one of those, either the direction or the magnitude, that's going to require a force. And for lack of a force, it maintains that. So, as I said yesterday, when I'm swinging this thing around and I let go of it, it's just going to go flying off in a straight line because that's what Mother Nature prefers. So, by virtue of the fact that this thing is continuously being pulled towards the inside, that means it's accelerating. And the direction of that acceleration, and you should have this twice on this assignment. When I asked you what's the direction, there's two parts to it. You say that force is going to act inward, and it's going to be acting at a right angle to your velocity vector. Okay? There's two parts to your answer. Inward and at right angles to the velocity vector. Because for lack of that force, boom, we're going to go straight. Okay. So, there's three potential sources of this centripetal force. So if you look at what's happening on number one, so these band members are marching around, but they want to maintain a straight line. So here's what you have to look at. Do you want to say something?
Maybe.
Okay? This is randomly walking. Okay? Okay? So here's what you would look at in terms of what you're going to hold constant. So if they're going to march around in a straight line, if you look at V equals 2 pi r over t. So the period for both of them is going to be the same, because that's the whole point. As they're going around like this, they're both going to take the same amount of time to complete that circle. So clearly the one with the bigger radius is going to have the bigger velocity. Okay? So, because they have to travel faster, because they have to travel a greater distance in the same amount of time. So the one on the outside is going to be going faster. So if you look at it in terms of your centripetal acceleration, well, that's 4 pi squared r over t squared. So again, the 4 pi squared t squared is a constant, okay? It's the same. So the bigger that radius is, the more centripetal force there is, the more centripetal force that you need, okay? So make sure on number one, you got all those calculations to do. Make sure they all have 3 significant digits, okay? So like I'm going to tell you right now, like on J and K, those are pretty small numbers. That's the minimum coefficient of friction that you need. Like let's say you have, I don't know, 0.004 is your answer. Let's just say that's one of your coefficient of frictions. If you have 0.004, how many significant digits are there?
One.
Just one. These zeros don't count because they're just taking up space. Now, don't go in there and go, oh, I'll just put zeros on the end. No, you have to look at what those values are. They're not going to be zeros, okay? But you just make sure that you have the correct number of significant digits. Okay, now let's talk about number 6 on the back, because if your answer to 6A is wrong, everything else is going to be wrong. So what's happening on number 6? So imagine me swirling this rubber stopper around over my head, right, like I did yesterday, and then I'm going to let go of it. Well, as soon as I let go of it, then it turns into a Lemming problem. Okay? It's a lemming problem. At its core, this is the beginnings of a lemming problem. So you know that it's 1.8 meters above the ground. So right away you can find time using 2D over G. That's how long it's going to take for that rubber stopper to fall to the ground. Whether I drop it, whether I project it out, it doesn't make any difference. So 6A should be around 0.6 seconds. Okay? Because if that's wrong, everything else is going to be a train wreck. So then on B, you're going to calculate the velocity, and C, you're going to calculate the tension. So on B, you're just going to use range equals Vx time. You know how long it's in the air. You know how far out it goes. You can calculate the Vx. So if all goes well on 6C, that answer should be pretty close to your age right now. Okay. Both of your answers on number 3 should start with a 1 and a 2. The decimal places are completely different, but
One-
huh?
One should start with a 1 and one should start
No,
with
yeah, number 3, both of them, the first 2 digits should be 1, 2.
Okay.
Decimal places are completely different, but yeah, both of your answers should be 1, 2. Start with 1, 2. Okay, anything on that assignment at all? Going once, going twice? Sold. So get that handed in. Okay, so you've got the lab. We're going to start this lab today, and there's no way we're going to get done. We're going to finish this up on Monday. So the good news is you don't have any homework over the weekend, okay? So that's a bonus. All right, and for those of you that are watching this, I'm just going to send you out the lab with all the data on it. So this lab is going to be due on Tuesday, okay? Lab is going to be due on Tuesday. So here's the basic idea of what you're going to do with this lab. So you're going to take, like, for example, a 100-gram mass, and you're going to hang that from the string on the bottom. So how this is going to start, you're going to take a piece of string, and you're going to securely tie the rubber stopper to the end of it. Then you're going to feed it through a glass tube, and then at the end, you're going to tie a weight to it. Okay, so in this case, I've got like a 100-gram mass. So this has become known as the cowboy-cowgirl lab over the years. Because what you got to do is you got to get this thing swinging around like this, okay? And then when you let go of it, that should suspend that weight. Now, if you change the conditions, like let's say, for example, if I slow that down, okay, to a different radius, then I can establish a new equilibrium, okay? If I go a little bit, if I speed that up a little bit, I can change that, go a little bit faster, I can change this, okay? So that's that's gonna be your technique. So here's the main assumption that we're going to make at the beginning, is that the gravitational force acting on the bottom weight is what's creating the centripetal force needed to make the rubber stopper continue on in that circle. So if you look on that data table, okay, so if you look on your data table, the first thing you need to look at is that, we're going to do 3 different things, okay, 3 different sets of trials. The first thing that we're going to do is we're going to change the amount of centripetal force, okay? So to find the value of your centripetal force, so here's this data table, okay? You're going to take the mass of whatever's being suspended, multiply that by 9.8, and that's going to get you your centripetal force. So if you've got a 0.1 kilogram mass hanging down, we're going to assume that that centripetal force is going to be 0.98 newtons. Because if I take 0.1 times 9.8, I get 0.98 newtons. And then you're gonna go to 0.2 kilograms, oh, we're gonna pay 0.2 times 9.8, 0.3 times 9.8, 0.4 times 9.8. So that's how you're gonna get those columns, okay? So that's the first assumption that we're going to make, is that the centripetal force is being created by the gravitational force, okay? Assumption number one. Now, what we're going to do is we need to calculate the velocity of the rubber stopper. So to do that, we're going to use 2 pi r over t. So you're going to have one person do the swinging, okay? You get this going like this. Now, the tricky part comes with the radius, all right? Because obviously it's going to be really tough for Kara to measure the radius of that rubber stopper if it's already moving. Okay, she's good at measuring. Okay, but that's going to be a tough sell. Okay, to get her to precisely measure that radius while Matt's swinging this around over his head. So what you want to do is, like, let's say for example you want a radius of 0.6 meters. So lay it out, put the edge of the middle of the rubber stopper at the end of the meter stick, and then measure here to 0.6. Then what you want to do is take like a marker or something and make a mark on the string, like so, okay? So what's going to happen, I don't know if you can see it back there, but there's that little mark right there. So what's going to happen then, when Matt or Shivani, whoever is going to be doing the swinging, what they want to do is they're going to get this thing going, so they're going to have that mark that we just made right there. So they're going to get this thing going until that mark that you just made is at the bottom of that tube. So when that mark gets right there, you know that you have whatever radius that you want to have for that particular trial. Okay? So the first 4 trials, you're going to keep the radius the same. And then you're going to change the amount of centripetal force. Okay? So let's look at the big picture here. So we know that centripetal force equals mass 4 pi. What we're going to do with this, well, let's do with mv squared over r. Hold on. It's going to be mv squared over r. So this lab is brought to you by this equation, mv squared over r. Now, here's the mathematical side of this. You're going to have 4 variables to deal with. Centripetal force, that mass, now listen to me. This is going to be the mass of the stopper, okay? This is the mass of the stopper, not what's hanging from the end of the string. That's the mass of the stopper. How fast it's going and the radius. So you have 4 variables: centripetal force, mass, velocity, radius. At any given set of trials, we're going to keep 2 of those 4 constant, and we're going to change the other ones. So on trials 1 through 4, we're going to keep the mass of the rubber stopper constant. That's going to stay the same. We're going to keep the radius a constant. Okay? So since these 2 numbers, mass and radius, are a constant, we can write this as centripetal force equals kv squared. Okay? I don't know what this number is. I don't care what that number is. Okay? We'll deal with that later. But here's what I want you to see. Y'all have seen equations like this dozens of times in your math classes. This is basically nothing more than y equals kx squared, right? It's a parabolic relationship. So here's what I want you to look at. So Kara, as that centripetal force gets bigger and bigger and bigger, so you're going to start off with like 100 kilograms and you go to 200, 300, 400. As this number gets bigger, there's more and more centripetal force. What's going to happen to the velocity?
Also gonna get bigger.
Yeah, it's also going to get bigger because these 2 sides of the equations have to be the same. Now, but are they going to get bigger at the same rate? Why not,
There's a constant in the equation that needs to be factored into that, and also.
No.
Oh, because the v squared.
Yeah, I'm squaring this side, and this is just centripetal force. So my centripetal force is going to get bigger and bigger and bigger. My velocity is going to get bigger and bigger and bigger, but they're not going to change in a 1-to-1 ratio because this is going to be v squared. Okay? Now, so here's the next thing. If you look at how you can calculate that velocity, that's 2 pi r over t. This is the circumference of the circle. So in trials 1 through 4, the circumference of the circle is going to stay the same. Okay, so the 2 pi r part of this thing is going to stay the same. So to get a bigger velocity here, what has to happen to the value of that period, which is how long it takes to go around? What has to happen to this number?
It'll get smaller.
It's going to get smaller. So what you're going to see is you put more and more weight on the bottom. You've got to spin it faster and faster and faster to create more and more centripetal force. And when you're doing that, T is going to become smaller and smaller and smaller. Okay? Now, here's the hardest part of this lab, and you may find this odd, but it is. This lab is an absolute home run. Where you screw up is your ability to count to 10. So what you want to do is get this hooked up. Okay, so there's my 100-gram mass. I've got my mark, right? I'm going to get this thing going. And you want to make sure that you're swinging like in a level plane, okay? Don't get something like this going where you've got like at a tilt, okay? You want to make sure that you are on a horizontal plane like this. So what you're going to do is you're going to get, who's ever doing the swinging, what you want to do is get it, kind of hold this, get it going, and then you'll feel that tension decrease, and then you're going to get it going like this. So after you get it going, everything's stable, right? You want to have at least 2 people, at least 2 of you, counting to 10 revolutions, okay? Now, don't count out loud, because that's poor form, because the other person's going to be trying to count, and then you're going to be going 1, 2, no, it's annoying, okay? Now, you can mouth it, and you're going to be behind a mask, and no one's going to see it anyway, but you can just do 1. Okay, some people get real intense like when they're counting this. So you're going to get it going, and then you're going to pick a point and you're going to count 10 revolutions. When you compare those times, if those times aren't pretty close together, one of you didn't count to 10. Maybe somebody counted to 9, maybe somebody timed 11, something went wrong, okay? So if you're off by quite a bit, just don't say, oh, we'll take the average. No. No, 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 no. One of you didn't count to 10. Now, if you're on real hardcore timers, you don't have to do this, but I'm just saying I've seen this done. They will actually like lay on the floor and look up and count that rubber stopper as it goes past a point on the ceiling. You don't have to do that, but I've seen it done. You know Tanner Singletary, okay?
He wasn't the one swinging it?
Huh?
He wasn't the one
No,
swinging
he was the one counting. His hair was getting in the way.
Nice.
So, and I nicknamed him Bruce. It's a long story. But anyway, so he would like, I've got a picture of him like laying on the floor like this, counting this as it goes around. You don't have to go to that extreme, okay? But the hardest part of this lab is actually counting to 10, as odd as that may seem.
That makes perfect sense.
Huh?
Makes perfect sense.
It is, okay? So here's what you're going to do in trials 1 through 4, okay? Now trials 1 through 4, you're going to keep this stopper the same. You're going to keep the radius the same. You're going to increase the centripetal force, so therefore your velocity has to get bigger, okay? So that's what's going to happen in trials 1 through 4. Now, on trials 5 through 9, okay, now we're going to keep the centripetal force the same. I don't care which, you're going to pick one of the masses from up above. I don't care which one you pick, 0.2, 0.3. I wouldn't do 0.1 and I wouldn't do 0.4. Maybe you want to keep that whatever mass that's hanging down, you want to keep the same in trials 5 through 8. That's a decision that you all have to make. But what you want to do is you want to change the radius. Okay? Now, and when I say change the radius, I mean change the radius. Like you want at least maybe 10 to 15 centimeter difference as you go through this. Now, because you're going to be making marks on the rubber stopper, if you want to start with like a new string on the next set of trials, you can. So that way, like the mark that you made on that first one doesn't interfere, unless you want to use that as one of your marks, okay, which is cool. You can use one of the radius that you set up from up above. If you want to keep that as your radius, hey, fine, fantastic, knock yourself out. But you want to get like a big variance in that radius, maybe from 50 centimeters up to a meter or something like that. You want a big difference in these trials. Now, think this through. So we're going to have centripetal force equals mv squared over r. We're going to keep the same stopper, okay? And we're going to keep the same centripetal force, okay? So this is going to be important. Now I'm going to keep the centripetal force constant. Maybe it's 0.2 kilograms, whatever one you want. 5 through 8, that side is going to stay the same. The mass of the stopper is going to stay the same, okay? So if you wanted to move this over, you'd have centripetal force divided by the mass of the stopper equals v squared over r. So this is going to be some constant, okay? You don't have to calculate it. This is just the mathematical model. This is going to be a constant, right? This number isn't going to change. So if you make the radius bigger, okay, Shivani, I'm going to make the radius bigger. I'm going to be dividing by a bigger and bigger number. But I want this to remain the same. So as this number gets bigger, and I want this to be the same, what has to happen to my velocity?
It has to get bigger too.
Beautiful, okay? It's got to get bigger as well, right? But is it going to get bigger in a 1-to-1 ratio?
No.
No, because again, this is squared. So on trials 5 through 8, you're going to keep the centripetal force constant. You're going to keep the mass of the stopper constant. You're going to change velocity and radius. On trials 1 through 4, you kept the mass of the stopper constant, the radius constant, and you changed the centripetal force and the velocity. So again, if you look at the trend on what should happen, when you look at your data, you could look and go, wow, is this going in the right direction? Now, on trials 9 through 12, over R, you're going to keep the centripetal force constant. That's going to stay the same. And again, you can use, on trials like 5 through 12, you can just take the same centripetal force each time. If you just want to use 0.2 kilograms the entire time, hey, whatever you want to do. We're going to keep the radius constant. So if you multiply this over, you would have centripetal force times the radius equals mv squared. So you could actually get this number if you wanted to, because the main idea is that this is going to be a constant. So Ms. Pfeiffer, this is a constant number on trials 9 through 12. This number isn't going to change. So if I make the mass of this rubber stopper get bigger, what has to happen to my velocity? Get smaller. So this is the only one that's an inverse relationship. Okay? So when you get to 9 through 12, you're going to tie different sized rubber stoppers onto the end of the string. Now, I'm going to have an electronic balance back there. That's how you're going to get the mass of the stoppers. Just set it on there, boom, there you go. But you're not going to change that until you get to trials, 9 through 12. And again, if you want, when you get to trials 9 through 12, you can use one of your data sets from up above, because you're going to have a radius, and you can use that mass as one of your trials if you want. Okay, so I'm done. We're not going to get anywhere near finished with this lab today. As a matter of fact, if you can get trials 1 through 4 done today, that would be kind of a cool deal. Then on Monday we'll talk about all the graphs and everything else about how you're going to answer this stuff. Okay? All right. Break.
What?
No, sorry.
fast. I definitely saw it go like in and out and in and out.
Yeah. There.
Nope. Okay. We're doing that again.
Alright, this heavy. Karen,
Your arm's
you
gonna
want
be tight now.
this? Okay.
You're doing great.
Okay, the weight didn't fall off this time.
It's true. Gotta give credit where credit is due.
Wait, I'm still not ready. There we go. Nope. There. Okay, I guess it messed up